All right, y'all. Hello, this is Mr. Garcia, and I'm going to be giving you your quick review on Coulombic forces and periodic trends. This is going to be everything you're going to need to know as quickly and concisely as possible so you don't have to watch a large video. So let's start off with the major thing that brings it all together, Coulombic forces. Those are basically the forces of attraction between a positive and a negative particle, or technically between any charged particles. So I can take my negative and a negative, or I can take my positive and my positive. And no matter which particles I'm taking, there's going to be a force as long as they are charged. So it's going to be the attraction slash repulsion between charged particles. Some very quick things that you need to know about them. If we look at the force versus charge, it is what we would say linear. As force increases, charge also increases. Force increases with charge. Sorry, I should say as charge increases, force also increases. The other thing to note is that the force versus distance graph, as distance increases, force decreases logarithmically. Oh, let me redo this curve one more time. There it is. As distance increases, sorry, this is exponential, increases, force decreases. I'm going to say exponentially. Why is this important? Well, what this basically means is if we look at our forces, if I double the positive charge here, then the repulsive force felt by this particle right there is going to double. However, if, for example, I have the distance here, the force of repulsion is going to be multiplied by 4. So, changing distance matters more than changing charge. And this point is going to come back. It's going to come back over and over throughout our periodic trend. So that's everything we need to know about Coulombic forces. So now we're going to hop right into my favorite trend, atomic radius. So if we go ahead and look at a picture of the periodic table, atomic radius is going to decrease going from left to right, and it's going to also decrease going from bottom to top. That's going to make helium the smallest. So a couple things. You would normally think as electrons increase, such as if we look at period 2, the electrons are increasing. As electrons increase, we would be like, well, they're on the outside, so why is this getting smaller? Well, the reason for that is, once again, Coulombic forces. If we look at an atom of beryllium, it has 4 protons, so I'm going to say plus 4, followed by 4 electrons. Gonna erase this little guy right there. And we have 4 electrons. 1, 2, 3, 4. Now, the thing is, as we move over to something, say, fluorine, well, we can see there's a little bit of a change. So I'm going to go ahead and actually just duplicate that one over here. Instead of 4 protons, fluorine has 9 protons. Looking at Coulombic forces, as the charge increases, the force will also increase. Therefore, with 9 protons, that's more charge. That's more than double the charge as beryllium. So what's actually going to happen is this inner ring is going to get smaller, and so is this outer ring. That's going to get smaller too, because there's 9 times the amount of there's 9 protons. Whoops. And so our electrons are a heck of a lot closer. Now, there are more electrons, and you would say, wouldn't they repel each other? But they're kind of pushing out this way, not so much that way. That doesn't really happen. So the 9 extra protons are bringing them in a lot closer. So if we go ahead and look at this size comparison now, let me just grab that, bring it right here, grab that, bring it right here. We can see that the beryllium atom is much larger than the fluorine atom. And so as we move from left to right, these atoms will get smaller. Now, as we go down the periodic table between like beryllium and then we can say magnesium, whoops, I don't even know what happened there, magnesium, you might make the same argument. Well, we have more protons. Shouldn't we have more force? Magnesium is not +4, it's actually +12. And you would think that, but the problem is magnesium has a whole nother energy level. It needs another energy level to contain all of its electrons. And that's going to increase that distance. That is going to increase the distance between the nucleus and the outermost electron. So if I look at this distance, the distance of magnesium is going to be greater than the distance of beryllium. And therefore, with that increased distance, we have a decrease in charge. That's the same thing we looked over right here. As distance increases, the charge decreases. And so that kind of explains why our atomic radius is getting smaller, but that decrease in force, that attractive force from the outside, is going to go ahead and explain our next trends plural of ionization energy, just to shorten that to IE, and electronegativity. Both of these have to do with that force of attraction between the protons and the electrons. Ionization energy is the energy needed to remove an electron. Electronegativity is the kind of amount that an atom will pull on an electron in a bond. So one of the requirements for electronegativity is that the atom needs to bond. And that's also why That requirement of the atom needing to bond is why noble gases, I think noble gases is 1s, have generally we'll just say a 0 electronegativity. So noble gases have a 0 electronegativity. So with that in mind, we're going to go ahead and look at our periodic table one more time. So as we look at our periodic table, we can notice a couple things. First, just a general trend is that as we move this way and as we move up, both electronegativity and ionization energy increase. I'm just going to say elect and IE increase. So the question now is why? And so I'm going to write that. Why? Well, as these atoms get smaller, we know that. So I'm going to use atoms getting smaller as a red arrow. I'll actually go ahead and kind of make it a really big red arrow. As atoms get smaller going up and to the right, that means the distance between nucleus, which is just the protons, and neutrons. But we don't really care about the neutrons, they're not charged. The distance between the nucleus and outer electrons shrinks. So as the atoms get smaller, the distance between the nucleus, the protons and neutrons, and outer electrons shrinks. And if we look at our chart all the way back here, I'm going to actually copy this chart because it's really important. So if the distance is decreasing, the force is increasing. And that force of attraction, the force of attraction increases. And with that increase, that means it is now harder to pull away electrons. It's harder to remove electrons. That's going to be our ionization energy. And any electrons that get close can feel a stronger pull. That's going to be our electronegativity. Because in bonds, these electrons are shared. Therefore, any ones that get closer to the atom with the stronger force will be pulled closer. All right, so that's a big unifying principle. So we're going to go on to the last thing, which is valence electrons. Valence electrons are just the outermost electrons, and they are involved in chemical bonding. So anytime elements bond, it's due to those valence electrons. And valence electrons are pretty easy to figure out, at least for the main group elements. So if we look at our periodic table, We're going to look at main group only. Which means I can go ahead and just kind of block some of this out. So we're not going to look at the transition metals or lanthanides and actinides. Instead, we're just going to look at the main groups. And it's pretty simple. For group 1, they have 1 valence electron. For group 2, they have 2 valence electrons. For group 13, they have 3 valence electrons. For group 14, they have 4 valence electrons. 15, 5 valence electrons. It's just whatever the group is minus 10 from 13 on. So this is going to be 6 valence electrons, 7 valence electrons. And lastly, the noble gases have 8 valence electrons, with the exception of helium, which has 2 valence electrons. That one exception, helium having 2 valence electrons, is because helium only has 2 electrons. It can't have more because it has 2 protons and 2 electrons, and therefore it takes up the outer ring. Because again, valence electrons are the outermost electrons involved in bonding. So if we use that definition and we go ahead and make our Bohr model for helium, go ahead and look at helium really quick. +2, 1, 2. And that's it. Their outermost electrons are the 2 valence electrons. And so that's it. Thank you and have a great night.